Thanks, Marco and Zena and Kush and Paul. Thanks to the organizers for inviting me. I'm very excited to be here. Slightly sad it's not in Eugene, I must say, but I'm very excited to be here because last time I lectured at OPLSS was 2021, and sadly it was online. So I'm very glad to be in a classroom and have all of you here. And so what I want to do, I have 4 lectures, and Amal already talked a little bit about program equivalence, and I think a lot of the lectures are going to, in some form or another, talk about program equivalence. And so what I want to do in my lectures is give you yet another way of thinking about program equivalence. And one thing I will do eventually, hopefully by lecture 3, is talk about program equivalence as a verification technique. So at some point, my end goal is to show you a language that's actually in use for network verification, in which program equivalence is used to decide properties like network reachability. But I'm going to build up that language starting from very basic concepts. And before I start, I want to run a quick survey. How many of you have seen regular expressions? Excellent. Deterministic automata. Okay, the notational semantics. Okay, and the operational semantics. I mean, you cannot say you haven't seen part of that because you have. But okay, so great. So I'm all set then. So here's a very sort of fundamental question, and a lot of what I will show, especially in these 2 lectures, I'm going to use a lot of sort of programs that look like real programs but are not real programs. So I'm going to use a sort of simple imperative language that has while loops, if then else, and then some program actions and some tests. So here's like 2 programs. One that uses 3 while loops on the left, and one that uses 1 while loop and an if then else. And the question is, if I just give you these programs, the things in red are some tests. I'm not telling you which variables I'm testing. I'm just telling you I'm testing something. And then the things in blue, P and Q, are program actions. So you could think of them as maybe variable assignments or something like that. But all of what I'm going to do for most of my lectures is going to be uninterpreted. So I'm not going to tell you which variables I'm actually touching. I'm just telling you there are some tests and some actions. Now, if I have these programs and I don't give you any more information, can you actually decide whether these 2 programs might be doing the same thing? Yeah.
Are the wires on the left nested? Or?
Yes, yes. Let me put some brackets around. Okay, let me put some end markers on this so that this is clear, what is nested and what is not nested. Okay, so there's a while followed by a nested while. Okay, so it's like 1 and then 1, 2. Okay, and here is just a big while with an if inside. Okay, and so the question is, would these 2 programs be equal for some notion of equal? I haven't told you what it means for a program to be equal, but all of you have programmed in one form or another. But so if you look at this, the question is, do you think there's any chance these are equal? Who thinks they might be the same? Okay. Who thinks they are not the same? Who has no idea whether they're the same? Fair. Okay, so what I want to do for the first lecture, or maybe lecture and a half, is give you a way to decide whether these 2 programs are actually the same. And so we're going to look at a language based on regular expressions that allows you to talk about equivalence of uninterpreted imperative programs. Let's call them simple. Okay. So by the end of this lecture, hopefully we can answer this question. Or maybe this will be homework for tomorrow. Okay? So this sort of question has been around for many, many years, reasoning about programs of this shape, so simple imperative programs with just while and if as control flow, and interpreted tests and actions. And if you look through some literature, you will find some of these already back in the 60s and early 70s. There's a very famous book by Mana on theory of computation, where a lot of it is devoted to studying these sort of questions. Then regular expressions, when they were introduced back in the 50s, they were also used then to reason about control flow of programs. And later on, there's been some research on something called program schematology, which, even though it doesn't look like this, it's in essence simple imperative programs. And what I want to show you, I want to talk about an algebraic approach to this question, so based on regular expressions. So to sort of set the scene, let's talk a little bit about regular expressions and what they are. And I'm going to keep reminding you of this as I go along. So regular expressions are a syntax. And you can think of regular expressions as a simple syntax to talk about regular languages. So the languages are the semantics. Okay? And in particular, the languages are the denotational semantics of regular expressions. And then there's a very famous theorem, which I will do formally in a moment, that says that regular languages are the same thing as deterministic finite automata. And deterministic finite automata you can think of, again, as semantics, but it's an operational semantics. Okay, so what I want to do for the next 15 minutes or so is define all these things, including this correspondence here, which is due to Kleene. Okay. Okay, so what are regular expressions? So regular expressions have some constants. I'm going to call those constants 0 and 1. And they are defined over an alphabet of letters, which I call A. This alphabet is finite. This will be important later on at some point. And these are sort of the basis elements of regular expressions. And then using these basis elements, you build more complex expressions by using the semicolon, which is sequential composition, plus, which is, you can think of it as choice, and star, which is Kleene iteration. Okay? Hopefully this syntax, modulo some use of symbols here is familiar. Okay, so now we're going to map. So we're going to take these regular expressions. Let's call this RE. And we are going to map every regular expression, E, to a set of words. And that's going to be my language. So I'm going to denote my set of words like this, to a star. Sometimes you see these written as power set of A star. Okay, that's a set of words. Oops. Let me just make sure that this is not annoying you. Okay, so what do I map 0 to? I'm going to map 0 to the empty set. So 0 is the expression that says I have no behavior. I'm going to map 1 to the set with the empty word, which I denote by epsilon. Okay, so this thing here, this is the empty word. Okay, and then I'm going to denote, to map A to the set with just A. And now let me make a pedantic remark. So the little a here, this is syntax. So there is, for every symbol in the alphabet, I have an expression for which I use the same symbol. But this is really syntax. This thing here, this is a word in A star that happens to only have one letter. But it's a word. And so this is a set with a word inside. So on this side, we have semantics. And on this side, we have syntax. And we sort of abuse notation and use the same letters. In my thesis, because I was very pedantic, when I introduced this in the preliminaries, I put underscores on every letter, which looked horrible. And this should never be done. But this is sort of like to remind myself that there's syntax and semantics, and it is important to keep them separate. For regular expressions, it doesn't make a huge difference, but later on, when we're going to talk about this extension for networks, it's going to make a difference. So we need to be a little careful about keeping these things separate. Okay, so how about so these are the constants. So how about the other operations? So there's one easy one, which is the plus. So if I have some expression E plus F, then I can just inductively say that the semantics of E plus F is just the union of the semantics of E and F. So I'm defining this set by induction on the expression. Okay? Okay, so how about sequential composition and star? What do I do with those? Okay, so for sequential composition, if I inductively compute the semantics of E, and I inductively compute the semantics of F, I have two sets of words, okay? And what I want to say, the intuition behind sequential composition is that if I do something with E, I then have to follow with something from F. I cannot just have the things from E. I have to have the things from E followed by the things from F. And so what I need here is an operation on languages that simulates this idea that everything from E is followed from something from F. And so this operation here, I'm going to define it. Let me see. I don't want to sweat this around. Okay, so if I have two languages, U and V, so these are languages, I'm going to define this operation as follows. I'm going to take any word from U and any word from V, and I'm going to concatenate the words. Okay, so here I'm using word concatenation. Okay, so again, this dot is a semantic operation, and it provides semantics to sequential composition. Okay? And now for the star, the idea behind star is that you do the expression 0 or more times. And you don't know how many times you do it. You might do it once, twice, 3 times, any number of times. Okay? So you just look at any possible natural number, and you say, for any number you pick, I can actually iterate E as many times as you want. Okay? And so here, I have this E to the n, which is an operation on languages that basically is defined inductively on n by saying, for 0, I have the empty word, the language with the empty word, and for n plus 1, I just concatenate Vn with V. Okay? Now, the star, as you see, is a slight relaxation from while loops. So the star says, I can iterate as many times as I want. So in some sense, you can almost think of the star as a while true do E, with a slight sort of simplification that I don't allow you to go really forever. I just want to look at finite prefixes of this iteration. Okay? Okay, so this is the notational semantics of regular expressions. Okay, so we've done syntax and we've done the notational semantics. And now I would like to sort of talk about this correspondence with deterministic finite automata and how to go from one to the other. Okay, but before I do that, let me just do a slight intermezzo. Find the examples. Okay, so let's write down a few examples of regular expressions so to see if we get the hang of what's happening there. And also because I would like to hear someone else's voice other than mine. Okay. Who wants to tell me what does this denote?
Empty string A, B, or A, B.
Correct. So I have, this is the empty string A, B, A, B. So it's a very simple finite language with 4 words. Okay? Okay, how about this one?
All sentences made of A or B.
Right. So this is actually AB star. So it's all words I can build with 2 letters. Okay. How about this one? This one requires coffee, which we didn't get in the break. So Marco, you're boycotting my exercises. What do we have here? Let's see. Who wants to try? There's someone in the middle. Oh, the same set as before. You mean AB star? Okay. Who disagrees or who agrees? Yes, back there. Same set as before, but no 2 B's can occur in a sequence. Okay, that's an interesting conjecture there. Nikos, you want to jump in?
No, I don't.
Yeah. That's okay. That's okay. Okay, someone else. I saw some other hands up. Maybe I ask Steve to. No. Okay. Yes? You retract your answer. Let me guess. Are you retracting your answer?
No, I think it's a sequence of B's interrupted by any number of A's, possibly 0, and then all A's at the end. Sure. Any number of A's, rather.
Okay, another one.
Are these examples the same as the example given at the beginning of the class?
Are these the same as the example at the beginning of the class? Now, here's another interesting conjecture. People are paying attention. Okay, you're on to me. Other, yeah.
We should convert these to GFAs and minimize.
Okay, let's see. I hope I didn't make a mistake writing that expression. But that, if you carefully look at the stars, indeed, you can write any word with A's and B's. It's a very weird way of writing any words with A's and B's, but it is a fact that, let me pick another column. It is a fact that these two expressions, A plus B star and A star, B star, A star, denote the same language.
Can you change color?
Oh, okay. I will. Let's go back to black. Black is well tested. Have a well tested situation here. So these two expressions are equal in the sense that their denotational semantics is the same. I'm going to write 3 bars instead of equal, just to distinguish this. So, okay, let me write 2 bars for now, and then I'll make the distinction in a second. I just want to go back to whoever said this is the same thing as the programs over there. In fact, this rule is known as the denesting rule for regular expressions. But this word denesting comes from papers back in the late 70s, early 80s on compiler optimizations. And indeed, what we will show, either today or tomorrow, is that there's a version of this rule that applies to programs that have tests and actions. And you can do things in there that, modulo, adding some colors here to distinguish the tests and the actions. I can apply the denesting rule to go from one program to the other, and a bunch of other rules. Okay, but now, this thing here that I wrote here, I wrote it on the expressions, right? And the thing is, I don't want to have to write double brackets all the time when I'm reasoning about programs. I mean, there are many program equations or regular expressions equations that are obvious. Like if I write 0 plus E, it's very tempting to just say, okay, this is E. And in fact, we know that from the denotational semantics point of view, this is sound, because the semantics of this thing is exactly the semantics of E. So what I'm going to want to do throughout these lectures as well is to show you that for regular expressions and for many extensions of regular expressions, you can actually come up with a finite number of these 3-bar equations. And I do this to distinguish, again, syntax from semantics. But I will show you that you can come up with a finite number of those to prove any equivalence of regular expressions. And later on, I'm going to show you can prove any equivalence of expressions with tests and any equivalence of expressions that have some networking constructs on them. And so this result, the fact that you can prove any equivalence from a finite number of such equations is known as completeness. And this was left open back in 1956 when Kleene proposed this syntax and this the notational semantics. He left open in his paper the question of, is there a finite number of equations that actually allow me to do program refinement? So back when he wrote his original paper, he thought of regular expressions as a special type of programs. And he asked the question, can I actually reason about them syntactically? Can I have these program refinement equations that allow me to reason about them? And the question was open for some years, and it has been answered in different ways along the years. So what I will show you, after we go through the automata, I will show you the axiomatization that was done in the early 90s by Dexter Cozen. But there are other axiomatizations, and I will leave some references also on Slack or in some of my notes. Okay? This is actually a very active research area where people look at extensions and how to complete these equations. Okay, so let's continue now with the operational semantics. I have until 5. Is that correct? Okay, so 5:10. Really? Okay. Okay, so what is this famous theorem that came to be known as Kleene's theorem? It says, let L be a regular language then the following are equivalent. L is the notational semantics of some regular expression E, or L is accepted by a deterministic finite automata. Okay. So let me talk a little bit about the proof of this theorem.
Or is a regular language just any element of power sets for a
Ha.
fixed alphabet?
Excellent question. Who knows the answer to that? Oh, sorry, thank you. The question was, what is a regular language? Is it just any element of power set of A star? And the answer is no. And I should have been more precise on this. Who knows the answer to that? Okay, so there's a notion of a regular set. So power set of A star is all the languages. And that includes languages like AN, BN, which are the languages of words that have the same number of A's and the same number of B's. And those are what is called a context-free language. Okay, so for those who haven't seen these, there's this thing called the Chomsky hierarchy. And at the very center of the Chomsky hierarchy, or at the very bottom if you want, we have finite languages. So these are languages that only have a finite number of words. Okay? finite languages are a subset of regular languages, which I will define in a second. And regular languages are a subset of context-free languages, and this goes on. Then you get context-sensitive languages, and so on. Okay, so and all of these languages are subsets of words. So they are an element of power set of A star. Okay, so what is a regular language? So in many modern textbooks, regular languages are just defined as the image of regular expressions. So that's one way of defining it. But that feels like cheating because I'm including the definition in my theorem, right? So originally, the way it was set up is that, so regular languages can be defined without referring to regular expressions. You just have to define the notion of a regular set. Okay, so for a set of words, you define when is that set regular. And that set is regular if it's built from the empty set, the set with just a word with a letter, and the empty word using concatenation, iteration, and union. So it's very closely mimicking the syntax of regular expressions. Or in some other way, the syntax of regular expressions was set up in order to mimic the notion of regular set. Okay, so regular sets have been around for longer than regular expressions. But really, they go hand in hand because the syntax of regular expressions was set up in that way to give rise to a regular set. And if you look at some older literature or even some more recent literature, sometimes the semantics of regular expressions is called rational. So there's a stream of research that sort of comes more from the French research community, where they try to distinguish between regular as a set and regular as in the image of regular expressions, and they call that rational, just to distinguish the two things. But ultimately, this refers all to the same thing, which is I have words, and I have sets of words, and those are built in a very restrictive way. They are built in a way that every time I want to reason about a regular language, I can break it down in finite parts. Okay, and those finite parts then enable me to prove properties about these languages. Okay, so I want to tell you a little. Yes. Oh, yes. Sorry.
Does Kleene's theorem establish a relationship between that E and that DFA, or
Yes.
is that implied by the fact that each of those are like the respective objects that are isolated by the equivalent conditions?
Right. So the statement does not. Oh, sorry. So thank you. I have someone here reminding me I need to repeat questions. Thank you. I make your job really hard. So the question was, does the theorem actually give me a connection between these two objects, the expression and the DFA that accepts the language denoted by the expression? And the answer is that the statement of the theorem does not really give me that connection per se. You could imagine that there's a proof of this theorem that is non-constructive, meaning it does not actually need to build the automaton. But the more recent proofs and the proof I want to show you, or sketch, actually does that. So I will show you how to go directly from an expression to an automaton. Okay? So I want to show you at least a sketch of both directions.
I think there's another question.
Yes. Yes. Could I write, so the question was, could I write the theorem like that? Is that correct? Yes, you could, because, I mean, because it's there. So in some sense, yes. Yeah. you can, in fact, it's probably a much better way to write it. I should not have written regular in the assumption. Good catch. Okay, other questions? Okay, so let me show you a little bit these directions. So I want to show you direction 1, 2, 2 first. Okay. So this proof I'm going to show you is due to a Polish mathematician called Brzozowski. I don't remember how to. I'm going to write it like this. I did know how to spell it, but I just forgot. So
May have some Polish students.
I know I don't want to make a title of someone who's very famous. And
What's the name again?
Brzozowski.
Oh, okay.
Is that first letter a B?
Yeah, it's a capital B. I probably have it written here in my notes, so I could just look, but I don't know if I have it in order.
All I know is it has to end with SKI.
Yeah, I know that as well. It's more what's in the middle. Okay, I will write it later when my brain helps me.
Shouldn't it be dot star SKI?
Good catch. Okay, so this proof is due to Brzozowski sometime in the 60s. And he introduced this syntactic way of building an automaton straight from the expression. Okay, and so this is the construction I want to show you. And then I will mention a list of constructions that are there in the literature that are also pretty classic. So the way he did that, he said, okay, I'm going to think of regular languages a little bit like functions. And I'm going to give it a notion of derivative. And this notion of derivative will correspond to a small step operational semantics. What does that mean? What is the type of a deterministic finite automaton? Who wants to help? So what do I need to have in a deterministic finite automaton? You all raised your hands when I asked if you knew what a DFA was. Okay, yes? And transition. Okay, so we have final states. So let's call that set final, F for final, which given some set of states. So I have a set of states, which is finite. So I have a finite set of states. So this is the definition of a DFA in sort of schematic way. I have a finite set of states. And I have a function that tells me, given a state, is the state final or not? Okay, I'm going to write this as a characteristic function. So given a state, gives me 0 if the state is non-final, and 1 if the state is final. And then I have a transition function, I'm going to call T for transition. And what makes a deterministic automaton deterministic is that for every state and for every letter in the alphabet, I give you exactly one next state. Okay, so you're not allowed to have undefined transitions, and you're also not allowed to have multiple transitions labeled with the same letter. Okay, so this type here is what makes a DFA deterministic. Okay? Okay, so these types of functions, so who here has programmed in Haskell or OCaml for that matter? Great. So whenever I give you, whenever you want to program something in Haskell or OCaml, what do you do first? You write the type of your function. And when I learned Haskell, the professor used to say, once you have the right type, There's nothing that can go wrong because there's only one function that will fit what you have in your head. In the age of LLMs, you know that this is not quite the case, but if you're a human and you have a certain intent, once you write the type, you more or less know how your function is going to go. And in some sense, this is what Jozowski sort of followed when he did his proof. He said, okay, if I want to build a DFA, I need to have a function that looks like this, two functions. And those two functions, if my proof is that I go from expressions to DFA, those two functions should operate on expressions. So what I need is a function that goes from expressions to, well, I think I used RE, regular expressions. I need to define a function that goes from RE to 2, and I need to define a function that goes from RE to A to RE. If I can define these two functions, I have a deterministic automaton. Still don't know if it's finite, but I have at least something that that has the right type. And then I need to talk about why, for every expression, this automaton is finite. Okay? But what do these functions what do they need to obey in order to sort of match my intent? My intent is that the language of the regular expression is the language accepted by the deterministic finite automaton. So when I'm writing this down in my little Haskell prototype of regular expressions, let's focus for a second on this first function, right? The function that tells me for any regular expression whether this should be a final state. What sort of intent do I have? What sort of semantic check do I need to do on my regular expression?
Does it accept the empty word?
Yes, does it accept the empty word? Because I know that if my expression is sort of allowed to terminate, meaning I'm at the end of recognizing a certain word, then the last thing I recognize is the empty word. If I have nothing else to read, then I have the empty word. Okay? So I'm going to call this function capital E for empty word. Okay? I mean, Brozovsky called it that, which was a great choice. And so what is this function like? So let's define it. I mean, there's not, once you know that that's what you mean, writing down this function is actually not very hard. Okay, let's do this for first. What is E of 0? False, so 0. I'm using 0 and 1 for false and true as well. What is E of 1? True. What is E of A? False, because A doesn't have the empty word. Now, what if I have a plus? So a plus is semantically a union. So if I have the empty word in the plus, that means that I have the empty word where? Either in E or in F. So this is like an OR. The plus, when I'm writing a function that has Booleans as the codomain, becomes OR. When can I have an empty word if I have a concatenation?
It's the and.
It must be both in E and in F, because the only way of getting the empty word from concatenating two things is from two empty words. Okay, so this actually becomes an AND in terms of Booleans. Okay? And finally, the star. True. The reason why I wrote this is because I wanted to just write the big, right? Because the star always has the empty word. Okay, so that was easy, right? Once we have the type, and once we know what we mean, what is the intent of that function, there were not many options in defining this function. Okay, so this is part one of Rozovsky's derivative. And now we have part two. Okay? I'm going to call part 2D because part 2 is really what is the analog of the derivative. Now, what is the idea, what is the intent behind D from a semantic point of view? So think of what an automaton does, right? So if I'm recognizing a word in an automaton, if I take a transition, what does that do to the word? Take something off, takes exactly one letter off, right? Every time I jump from one state to the other and I read a letter, I'm sort of deleting one letter from my recognition. So semantically, on languages, I'm just going to write this here. If I have a language, L, if I have a language L, if I write L sub A to mean the derivative of this language by letter A, what I mean is that I have the word AU in my language, and I just remove the A. Okay? So the derivative is with respect to a letter, and it just tells you what are all the continuations after I delete this letter. Okay? That's the intent. The intent is to syntactically define a function on regular expressions such that, I'm going to write it like this, D of A, such that for every regular expression, I produce another regular expression that the language is this language L of A. Okay, so that's the intent. So this is a little more complicated than the empty word test, because we need to manipulate the expression, which is syntax, to give me this semantic intent. Okay, so let's see how we do that. Let me find an empty board. Okay, let's go back to black. Okay, so I want to define this function. And I hope it was clear that what I did here is go from a function from, so if I have a function from x to xa, a function from set x that takes then an a and returns an x, this is the same thing as a family of functions from x to x indexed by elements of A. And here the fact that A is finite is important. The fact that I can sort of switch between families of functions and defining a function. And notationally it's just a little nicer because it really gives you this idea of derivative. Okay? So let's just think about the base cases, okay? Like 0 and 1 and a letter, which I'm going to denote by B. If I try to remove an A from the language denoted by 0, what do I get? 0. If I try to remove an A from the language denoted by 1, which is just the language with the empty word, what do I get? 0. Okay? But if I have a letter, B, and I try to remove an A, then I have two cases, right? If A is equal to B, I do one thing. If A is not equal to B, so if A and B are different letters, then if I try to remove an A from B, I get 0. But if I try to remove an A from A, what do I have left? 1, the empty word, right? So I'm writing the syntax, but in my mind, I'm sort of thinking about the semantics. Okay? Now come the more interesting cases. what happens when I have a concatenation. This is, in my taste, the most interesting case. How can I remove an A from a concatenation? Yes.
We have to do case split when it's empty.
Yes, we can do case split. So what would the case split be like?
You can either remove an A from E, or if you essentially remove A from E.
Okay, so I'm going to slightly rephrase what you said, just to be more precise. I can either remove the A from E, totally correct, or if E has the empty word, then I can remove an A from F. If E is empty, then I cannot remove anything from anywhere. Okay, so we need to be a bit careful to distinguish between empty and having the empty word, because these are two different things. Okay, so if I remove an A from E, I remove an A from E, but what do I need to be careful about? So this is the case that I remove the A from E. What do I have left? F. Right, so this is the expression that tells me I've removed an A from E. All right, and then I continue with F. The other option, and I can write this syntactically as plus, is that I did what? I had an empty word in E. How do I write that as an expression? It was an idea. We have this test, right? This E. And we wrote it as a function from, a function from regular expressions to 2. Okay? And here's the cool trick. 2 actually embeds back into regular expressions. That's why I've used the same 0 and 1. Because the zeros and ones that we wrote here, they are Booleans, but in fact, they are also regular expressions. And that it so happens, if I write these as, I take the A from F, guarded on the fact that I did have the empty word in E, a cool thing is going to happen syntactically. If he did not have the empty word, this ends up being expression 0, okay? But as it turns out, if I concatenate expression 0 with anything, what is this going to be equivalent to, semantically and syntactically? To 0. And 0 plus anything else is also that thing there. So this function, I could write probably in the way that you intended, which was as a case split. So I could write it as a case split that tells me this one is the case that E of E is 0, which tells me I will never be able to take anything from F. Okay? And this one is the case that E of E is 1. So I could write it like this, but I can also just write it as a plus. And here, we sort of start seeing a little bit where I want to get to, which is the connection between if then else and regular expressions. Oh. Let's go back to some other pen about red. So if then else is really going to be connected to the plus of regular expressions. Not in this lecture, but tomorrow. Okay? And this sort of is reflected in the way this derivative would be defined. But I prefer to a compact version, so I'm going to leave this here. It also gives me more board space to write the other case. Okay? This is for tomorrow. Okay, so this is really the interesting case, because if you think about the plus, there's really not much you can do other than writing the only thing that is type-wise obvious. And then maybe the star you could think is interesting, but the star is nothing else than a simplification of the concatenation, right? So what is the star? The star is either I do 0 times and there's nothing I can take, or I do E once and then I do E star again. So for the star, the only thing I can do is hope that I can take an A out of E, and remember that I can continue doing other things, okay? So these two functions, E and D, give a automaton structure to the whole set of regular expressions, okay? Now, the whole set of regular expressions is not finite. So this is not a deterministic finite automaton. So I'm not quite there yet to have the proof of one direction. But I'm almost there. So what do I need to show? Who has ideas? Once I have these functions, I have this ginormous automaton that has all the expressions in there. My theorem says, the direction I'm trying to prove says, I have the language of one expression, and I want to build a deterministic finite automaton from it.
Can you prove that the language's set is a subset of that infinite set?
Almost, yes, you're going in the right direction. There was someone here in the middle when I asked what is a deterministic finite automaton that gave one more element that I did not include on the board in the definition of DFA. The start state, someone said this here. So what I built here is this enormous automaton, but has no start state. So that's the beauty of this automaton, is that I can now pick a start state. In particular, I can pick E as my start state. Okay? So now I have this enormous automaton, but I picked E as my start state. And from E, I start going and collect the states I can reach. Okay? And ideally, I would be able to argue that the states I can reach are finite. Okay, this would end the proof. Does everyone agree? I have this infinite automaton from which I can pick any E as start state. And if I can prove that the subautomaton that I can reach from E is finite, then there's that. I've built my automaton. I also need to prove that every state in this automaton accepts the language that I wrote as the state name. But that's sort of immediate from the definition of D and E. Okay? So the real missing piece is the finiteness. Okay, who thinks that this is true? That if I start from an expression E and I turn the crank on D, I only get a finite number of derivatives or states. It's a question. Who thinks it's true? Is that you were answering? Okay, sorry. I thought you had another question. Everyone knows that if I'm asking this question, it's because it might not be true, so no one dares raising their hand. Okay, it is not quite true. It is almost true. So let me see if I was smart enough to write a simple example in my notes, or if I have to come up with it. Okay, so here's an exercise. The exercise is, what if I give you the expression A star star? What can I encounter along the way? Now I got to the part of my notes where I actually wrote his name, so I can. Okay, I'm going to cheat a little bit and just give you the answer. So if you do the calculation, what you get, so if I call this E, what I get as D of A of E is this expression, okay? Then I need to copy my notes, otherwise I'm going to make a mistake. If I do again now another A, I get 0 A star. Okay, let me write it. Okay. So what's happening here? So these are the first two derivatives. Okay. So I take 1A. Okay. And what do I get? Well, I took an A from A, the body of the iteration, and I got the empty word because I removed the A. I'm left with A star after I removed an A from here. And then I'm left with A star star. Okay, this is applying, it's basically applying this rule here twice. Okay, because I do dA of A star star, which gives me dA of A star concatenated with A star star. So I get this expression, and then I do it again to obtain the next state. And when I do it again, I try to take an A from 1. So now this is a concatenation, right? So I try to take an A from 1, which ends up failing because I don't have an A left there. And I continue with A star. Or I take an A from A star, which succeeds, and I continue with A star. Okay? And I need to remember to continue with A star star. Or I use the fact that this expression has the empty word, and I take an A from the second expression. And that's this thing here. Because when I take an A from the second expression, is actually this expression. Now what's going to happen is that this expression here is going to keep showing up. Every single time I'm taking an A, I have the option of taking an A from A star star. And so what I'm going to end up with when I do the third option, the third derivative, I'm going to end up with a bunch of things plus, let's call this expression F, plus F, plus F. And every time I go plus F, plus F, plus F. And staring at it, you say, but it's just the same thing. Plus F is just F. Why do you keep taking more derivatives? Well, because this function D is oblivious to that equivalence, right? This function D only knows about plain syntax. This function D does not know that 1 concatenated with A star is just A star. Or that 0 concatenated with A star is just 0, should be thrown out. And that 0 plus something is just that something. So this function D is, from an implementation point of view, not very smart. It's sort of like keeping around lots of useless terms. Okay? So in order to get the finiteness, or to get the finite automaton, what do I need to do? Ideas?
Look at equivalence classes of derivatives.
Yes. Look at equivalence classes, but what equivalence? So there's a minimum you can do, and there's a maximum you can do, and there's things in between. And they all give you finiteness. So I can take, so the minimum you can do, the bare minimum, is every time you take a derivative, you need to delete any repeated terms in a plus. If you delete any repeated terms in a plus, you're done. You're good. You get finiteness. That's the absolute minimum you can do. That, deleting the repeated thing, is just guaranteeing that I don't keep growing my term with equivalent terms. The proof in Brzozowski's paper goes a bit further and says, take the derivative modulo ACI, associativity, commutativity, and idempotency. So that means that idempotency would basically delete this F, because it would tell me F plus F is F. Associativity would just allow me to sort of not write brackets, which I was already doing here, because I did not write the fact that, maybe this bracket is like this. I sort of just wrote the sequence of pluses. And commutativity just allows me to sort of flip the expressions when I'm doing the plus. Okay? Now, doing the reasoning, modulo associativity, commutativity, and idempotency, is actually equivalent, was shown a few years later, to, instead of writing E plus F equals D of A of E plus D of F, we could have written this as a set. I don't know if everyone can see this. But basically, I was insisting that every derivative gives me exactly one expression. If instead I would have been happy with getting a set of expressions back and then put them back together as one expression, I would get associativity, commutativity, and idempotency for free. Why is that? Because if I map my plus into a set, if my two derivatives are the same, when I map them into a set, it just becomes a singleton set. Because you get for free both the associativity, the commutativity, and the idempotency in this way. Okay? And this is what is called, so this is another proof that is due to Antimirov. Okay? That basically says Brzozowski went out of his way to prove finiteness in a syntactic way by then sort of doing the reasoning. So just to be precise, let me not write the power set here. So Brzozowski proved finiteness by saying that he's reasoning modulo ACI, so he's looking at equivalence classes. And then Timirov basically said, well, but that's nothing else than just taking sets of derivatives. So you didn't have to reason syntactically. You could have simply taken sets. Okay, there was a question somewhere. Two questions, yes.
You said that plus, for example, was just syntax. So we cannot say that a plus of two identical things, but in a set of, for example, F plus F and F, but in a set together, it's still a set of two regular expressions, right?
Correct. If you have F plus F and F, you still have that problem.
I don't exactly see how we get idempotency.
So I said that the minimum you need to do to get finiteness is to delete the top level repeats. So you don't need to reason modulo ACI all the way down the parsing tree. You just need the top level. And that's why if you put a set with, as you're building your set, you will never get that situation unless you're at the end. Because otherwise it would have been washed before. Yeah.
So the second derivative, should there also be a, is it a 1 sort of concatenation point of the f then? By definition?
In the one in front of?
The f term. Because you should include, so in the first derivative, so the e of this thing should give 1, and then when we write out the syntactic derivative
Yep.
of the
Yeah, there should be a 1 here, you're right.
Do we also need then an equivalence theory for like removing these 1s?
No, only the plus is a problem. So you end up writing a lot of things. So the absolute extreme is that you take all axioms that I will show that would quotient all expressions to a minimum. Yeah. Oh, the repeat. I forgot the question. Can you repeat your question and I'll repeat it? Oh, sorry, I remember now. I forgot a 1 in the derivative here. And the question was, do I need to also remove the 1s to get finiteness? And the answer is no. But the automaton you end up with is far from minimal. To get the minimal automaton, you have to do all kinds of quotienting. Okay. But for the proof, I don't need the minimal. I just need to know that there is some finite automaton. Okay, so I have a couple of minutes. Let me see. Oh yes, I said I would mention at least one alternative proof. One is Antimirov's proof. Okay, in Antimirov's proof, at the very end, he actually goes back to. So what he obtains is a non-deterministic automaton. And at that point, he needs to determinize it. And in his proof, he determinizes it by just writing down DAE plus DAF once he has eliminated all the repeated elements. So he takes the automaton, which is non-deterministic, but the states are labeled by expressions. So he can then do determinization syntactically. Okay, so whenever he has an expression E, so let's say, sorry, E plus F, and this will generate dA of F, and maybe, maybe F, maybe F is again a plus. So maybe here I have E plus F plus G. And then here I continue, and I do some things. dA of F, and dA of G. And so maybe when I'm doing this, maybe it turns out that dA of F and dA of G are the same thing. So in his construction, these states will never be seen because it got absorbed by the set, okay? But this is still non-deterministic because in this first transition, I was not able to eliminate anything. So this is not a DFA, it's an NFA, a non-deterministic finite automaton. And what he does in his construction, once he's done eliminating all of this, he has a finite non-deterministic automaton that accepts the right language, and he just says, well, now I have the names of the sets that happen to be regular expressions, and I've already guaranteed that everything is finite, so I can now do this nice peanut thing here. and put a plus. Okay? And now this is just one transition to the peanut. Okay? And he does that, and that's it. There's a syntactic, again, automaton that accepts the right language. So that's Antimirov construction. What you see most of the time in textbooks, and you might have remembered this, is called Thompson's construction. Thompson's construction is more operational in some sense, and it uses, I mean, if you've seen this, sort of like, let's take E and F as a sequential composition as an example. Thompson's construction says, okay, you have some automaton for E. Let's write it as a box. What I know about this is that it has an initial state and potentially some final states here, and then something in between that I don't care for a second. And then I have something for F that looks a bit like the same. And now from these two little boxes, I'm going to build a bigger box. Namely, I'm going to say, when I'm finishing in E, I'm not allowed to finish. So I'm going to turn this into non-final states. And I'm going to allow you to jump to the initial state there. But what do I read when I jump to this state? I read nothing. And so Thompson's construction allows you to use empty transitions, or transitions labeled by the empty string, and shows how to inductively, from two automata, build a bigger automaton. So it's a translation that really directly gives you the automaton. And it starts by saying, you know, if I have 0, that's this automaton here. Let's say it's over the alphabet AB. If I have 1, that only accepts the empty word, then I have this automaton here. If I have A, then I have this automaton here. Okay? And so it sort of builds, does an inductive construction directly on the automata. And then for every operation, it shows you how to build a new one. Okay? And then, you know, for plus, it says, okay, you have again one of these little boxes for E, a little box for F. And if I want to do E plus F, I just add a new initial state. And I allow you to choose where to jump. Okay? Now again, Thompson's construction sort of lands you in the wrong type. It gives you a non-deterministic automaton with epsilon transitions. So then, to use it in the proof of Kleene's theorem, you need to show that for every non-deterministic automaton with epsilon transitions, I can build an equivalent deterministic finite automaton. And this is like the sort of thing you see in a classic theory of computation book. Epsilon elimination, determinization, all of that. And so that Thompson's technique is really what you might have seen in the past as a proof of Kleene's theorem. Whereas Brzozowski's proof or Antimirov's proof is more what you see sort of in research in this area, because they are more direct and more syntactic in some way. Okay, I think I'm running out of time. Yes, 5:10, precisely the time Marco gave me, and I can do this, except I didn't only gave you one direction. I will talk a little bit about the other direction tomorrow. And I'll take a couple of questions, but if you're too tired and want to go to dinner, that's also okay. So yeah, this is the end. Thank you.